Started. Let's get started. So what you're looking at now is D2L. You guys all know how to use D2L? I hope so. Everything in this course will be on D2L. I will try and put everything on D2L. So you can see there, this is our page for our class only. And so I got a couple of links there. When I hover over them, you can see that those links do something. There's a bunch of notes there that I put up there. Those are notes which are the result of a meeting that we had with all the instructors for this course. There's lots of instructors because there's lots of course classes. And so this is the way that we want to have all the classes the same. So these notes are how we're going to do it. So you'll see that we're going to have a lecture, which will be the first lesson. Yes. Hafsa, your name is not on the list. Hafsa, I saw your name on a list. So maybe it's on this list. Zobia is here. This section 18, 17. Yeah, so you got the wrong list. That's why. Maybe that's why you couldn't find it. This is my other class. Yeah, it's all right. Just tick it off that. Don't worry about it. Sorry about that. I don't know how that happened. Okay, so this bunch of instructions here, make sure you familiarize yourself with all of those instructions and you know what's going on there, all right? We are going to have a lecture. Will be this lesson every day, right? Sorry, every week we'll have this lesson will be a lecture. Then we'll have a tutorial, the next lesson. Then after that, we'll have a lab. All right, now the tutorial and the lab are assessments. Kind of, I'm not sure as much about the tutorial. I think we'll run quizzes there too. The lab, you have to work by yourself. You're not allowed to copy anybody else. But during the lab, I can come around and help you. You have to finish the work during the lab. So the lab is not take-home work. The lab is do it in class. So you come to the lab, I look at it, that's when I mark you. That's how way it works. The lab, you'll be given an exercise to do, and it's a timed exercise. You've got an hour and a half to write a little computer program kind of thing, or some other exercise. Okay, so that's how the lab will work, and you'll be assessed on that. And you'll have to submit the lab to D2L. So you'll see in D2L, we have a bunch of different assessments. We have drop boxes, and that's where I'll be putting all your labs. Right now, the other things we've got in D2L is we've got quizzes, and that's where we'll be having all of our quizzes. Quizzes will be every other week. So once every 2 weeks, we'll have a quiz. We've got 2 tests, 1 test in week 5 and 1 test in week 11. Then we got a final exam. So we got a lot of stuff, right? And so the final exam will be in the final week, right? And the final exam is 30%. The 2 tests are 20% each. The quizzes all add up to 10%. So the quizzes are little. The quizzes are open book. The final and the tests are closed book with lockdown browser. So you won't be able to sort of have any help with those. Correct? Yes, you will be having multiple choice questions. In the quizzes will mostly be multiple choice questions with some short answers. Likewise in the test and the final. The final, you'll have to write some computer program, write some Python code on paper, and probably draw some flowcharts. And maybe in the tests also. Okay, good luck. No. Find a friend. No, I actually, that is also my job. But so we try and make as much help as we can. You can come and see me. I will try and help you. The other thing that you can do is we do have peer tutors. So that's not started yet, but basically what happens is lecturers are asked to nominate students that they know from last semester who are really, really good. And I think they get paid or something. I don't know. There's some kudos that goes to them, and they will come and sit in a room and help students doing stuff that they know how to do. So there's that, but you can always ask your lecturers. My contact is available on this course syllabus that we'll look at in a second. You can come to my room during my office hours. The other thing is I have left my phone number there. So now the reason why I left my phone number there is I'm not expecting a lot of people to call me up. If it's an emergency, okay, but I can't think of what that emergency would be. But I'm not expecting that. But what I don't mind, and I found that this works with most of the classes, is students will form a WhatsApp group, and for the class, call it WhatsApp INFS1101 and something section 18 or whatever, and then they invite me to join the group, and then they put questions on there and I answer them. So that works. And so that I like that, because that way you have a question, and guess what? Somebody else has the same question, right? And then I answer it once and everybody gets the answer. And so, yeah. So there's a couple of ways we can do it, right? So, so there's more than one way of helping. But certainly you can come and visit me if you want to, if you feel that would work better. So yeah, on that point, I do have this document here. I'm not handing out lots of paper. You see that? I'm trying to get you to get the idea of using everything on D2L. The other thing is you're enrolled in 2 different courses, sort of, or no, it's one course, but with 2 sections. Did you notice that? You're enrolled in section 18 and section 17. And so you actually have D2L for section 17 and section 18, right? Is that confusing? All right, so to make it less confusing, we'll only use section 17. Right, everything will be on section 17. You see, this is section 17. All right, I won't put anything on section 18. So everything will be there, all your labs, all your tutorials, all your lectures. So the idea of the 17 and the 18 from the college point of view is 17 is for lectures, 18 is for labs. But you have the same instructor for lectures and labs. So it's me. Sorry about that. So we have to, so the idea was that you could have a different instructor for labs, and yeah, they might do that in the future. But at the moment, it's the same instructor for lectures and labs. So that's why we're doing it all in 17, okay? Okay, so this document here, which I'm not giving to you on paper unless you ask me. Now, I don't want to seem like I'm really mean or anything like that. If you want me to print papers for you, I'll print papers for you. But I don't think you need it, do you? Hey, you're just going to throw it away anyways, right? So it's there for you on D2L, and you can read it anytime you want. If you want, come and ask me, and I'll print it out for you. Not a problem. But it explains there what this course is about, and that is a new course. We've only been running it for the last semester. We've actually changed a little bit of it up this semester just to make it a bit better focus on the lab part. That's the only part we changed. We haven't actually changed the theory at all. We've changed the lab a bit. There's my contact. And as I said, if you WhatsApp me into your group, I will answer questions. You don't have to. I mean, maybe you don't want me to talk to you. That's fine. But if that would help you, then go ahead. So there's this is kind of like a contract. So it's kind of like, okay, this is what we promise that we're going to try and do, is we're going to give you learning opportunities so that you could learn this stuff. Now, we're not promising that you're going to learn something, right? I mean, because learning, you have to do it. I mean, what I can do is I can give you an opportunity to learn, right? And do my best to provide you with learning experiences. But you have to do the other part, all right? But if you did the other part, then my promise to you is I'll give you opportunities to learn this stuff, okay? So that's what that's about. And then not only will I give you opportunities to learn this stuff, but then I'm going to give you an opportunity to show that you learned it. That's going to be called an assessment. And this is how we're going to assess it. Okay, so you're going to have assignment, quizzes, tests, and exams. And that's where you're going to show how you learned all that stuff. And there's a lot of them. And so that's how we're going to, in the end, you'll get a mark. And the mark will be somewhere between 0 and 100. And you'll have to get 60 or more to pass the course. Out of that possible of 100, I'm not giving, okay, so I have heard this happen. Bonus marks. Yeah, forget all that. All right, it's not happening. All right, so the marks are here. come and get the marks, right? Yeah, they're here. You'll have a chance to get it. I try and mark fairly, and I'll give you every opportunity to do the mark. But the course is not out of 120%, it's out of 100%, okay? So 30% for the final exam, 40% for tests, 2 tests, 20% each. A bunch of quizzes, bunch of assignments, and labs. Now notice there's a bunch of quizzes, bunch of assignments, bunch of labs. The labs, you have to do them during class. Look, you know what? You do the lab, you can't do it. You ask me, I help you. You finish, you get 10 out of 10. Okay, you get the idea? All right, you do the lab, you get the marks. That's the easiest way of getting the marks, is just doing the lab. Assignment and quiz is a little bit trickier, but you know, the quiz is open book. You can have your notes with you. I mean, the only thing you can't do is ask each other for help or ask me for help during the quiz. But any notes you got, you can use them. The tests and the final exam, there's nothing, no help. All right, so it's going to be lockdown browser and you know all the rest of it. So it's very, very tight, that one. So hopefully that'll help you. There's the plan, how we're going to do it. So this week we got 3 things, right? I don't know how far we're going to get in labs. We do have a pre-lab exercise that I can give you during the lab, but I don't know how far we're going to get with the lecture, because here I am talking to you. It's not a lecture yet, is it? You know, it's just me introducing the course. So I don't know how far we're going to get with the lecture today. I might have to steal some of that tutor time and lab time to finish the lectures up. But yeah, the looks like 2 lectures to me, right? We got to do the history of computing and computing nowadays. That's a bit of stuff to get through. So we're going to start on that today. We won't start on the pre-lab exercise. We'll do that in the lab time. So looks like we might do this during the tutorial time as well. But you'll see the other things that we're going to do. Look at that. We got a quiz coming up next week. And a lab. All right. So yeah, we do sort of get cracking pretty quickly. And then there's a bunch of rules and regulations. Later in the course, we're going to be using Python programming language. You need to have a computer that you can write Python programming on. So you need to be able to install the software to do that. The software is called IDLE. If you go to python.org, just Google it, python.org, you can download the latest version of their IDE. And it's free. Nobody's going to ask you for any money. Just download it, and it's free, and it's virus free also. I mean, you know, this is proper professional stuff. We're not pirating anything or anything like that. This is how we do stuff. I mean, it's good software. You can download that. It's safe. Put it on your computer, and you'll be able to write your Python programs. Yeah. Python like a snake. .org. And in fact, they have a snake as their symbol. So python.org, go there and download their stuff. So it's .org. So it's not like .com, right? It's .org. So you know that that's sort of like it's an organization. It's a group of people that are helping each other. It's not a company that's selling stuff, right? But it's a big group of people. I mean, you know, there's programmers from all around the world. I mean, it's not some guy sitting in a little kitchen somewhere. I mean, this is a lot of people. And so it's professional software that you can download and learn how to write programs. Now, I bit my tongue there because I might have said simple programs, because when you look at Python and you compare it to something like its predecessors like C, yeah, Python looks maybe simpler, but it's not as simple. It's not baby language stuff, all right? I mean, you can do a lot of stuff with Python. People are using Python for program computer networks, okay? There's a lot of stuff you can do with it. It's a proper programming language. But if you just want to write little small programs, it's kind of easy to get started in, because we don't have to do a lot of curly braces and stuff like that. We don't have to declare our variables like you do in other programming languages. Like with C programming language, you have to declare all your variables with the correct type. We have to declare our variables, but we don't have to type them as we declare them. And C, that can get a lot of people into trouble because there's a lot of sort of issues regarding for new programmers. So Python is sort of forgiving for new programmers, but it's a proper object-oriented programming language. Does that mean anything to you? I don't know. You know, so you can create objects and classes and methods. And yeah, it's not toy stuff. It's real. You can make a proper big project with it. It's pretty good stuff. All right. And then there's some stuff there about how we do our, all right. So, okay, you have to hand in the labs during the lab time. We do give you penalties if you don't hand stuff in on time and stuff like that. So sorry about that. And there we go. And there is my timetable. So I told you, look at that blue time. I'm in my office then. I'll try and be in my office then. But actually, a lot of this white time, look at that. I have to come to work at 10 o'clock this morning. Actually, I came like 8. It's going to be long by the time I get home, right? But, you know, I'm not going home during this time. So I might be out walking around the college, or I might be having my lunch, but I might be in my office too. And I don't mind if you come and see me. So, but maybe in this time before 10, might not be around. Don't come looking for me on Thursday afternoon. I can tell you where I'll be, and it won't be in my office. All right, so yeah. So, but you're welcome on the other times. All right, so that's enough on that, I think. So that document's there. As I said, anybody wants me to print that, I'm quite happy to print it out for them. But I think that you don't need it because it's there for you. You can look at it anytime you want. None of this stuff that's on D2L is going to go away. It's there. Right. Once I put it up, it's there. So that brings us to our lecture for today, which is also there, which is about the history of computing. And the idea here is not to turn you into history majors, but it's so that you have a bit of a context of understanding sort of how computing sort of evolved to the point where it is now, and where computing fits in the rest of the world, right? You know, so what is the idea? What is it? It's a fantastic industry, really, isn't it? I mean, so it's employing so many people doing so many interesting things in computing. And, you know, so how did we get to that point? Here's where we start talking about that. So we've got some sort of mechanical devices that we use. This is all mechanical devices until everything before this is our mechanical devices that we used to do computing. And the first one you might recognize is Abacus. Still people use those a little bit, but they've been around for a long time, like 3,000 years, right? Slide rule, not quite so long, been around for a couple hundred years. I used a slide rule, so some people still using Abacus. I was using a slide rule in 1970s, 1971, 72. Yeah, we're using slide rules. I didn't get a calculator until like 1978. First time I saw it in a university, I was at university. There in the bookshop, there's, oh, look at that thing. It's a calculator. I don't have to use a slide rule anymore. I can just punch in numbers. Wow. Anyway, so they didn't really, those calculators didn't really come in until the 70s, late 70s. Babbage made a machine that's kind of like a big clock, except the gears are a bit different, and you could use it for doing multiplication, division, addition, subtraction. Hollerith, he helped to do the census, so he had a machine that read cards, so you could add up things about a bunch of people, where they were living. That's how a census works. The transistor, the idea of a transistor is taking the electronic gates that were in the old computers and making them smaller and more efficient. And so our transistor radios that showed up in the 1960s, we see the transistor was invented, it says there in 1947, but the transistor radios sort of showed up in the 1950s, 60s. And yeah, the idea is we got our electronics were smaller and used less electricity to do the same thing. Big breakthrough here with Steve Jobs and Wozniak when they introduced the Apple Mac. What was so amazing about it is that we had this graphical user interface. So the graphical user interface is more intuitive. What I mean when I say it's intuitive is people look at it and they kind of know what to do without you having to tell them. Right? They look, oh yeah, I know how to do that. Look, there's a mouse. And you know, you've seen that, right? You know, you got the 5-year-old kid that sits down to a computer and starts playing computer games. And 10 minutes later, they're faster at it than I am. and I've been doing computing for like 100 years, right? So I mean that's what we mean. We got computing has become sort of intuitive. The interface between us and the computer is easy for people to understand. It's in the computer is gone to the place where the people are instead of the people having to go to where the computer is. Let me show you what I mean by that. Let's see. So when I started computing, this is how we said hello to the computer. We had a screen that looked like that. Okay. Well, what next? All right. So if I want to do anything, I have to type a command, and I have to know the command, right? So you know, and you know, how exciting is that? You can still use this. This is called a command line interface. Command line interface. You have to type all the commands. If you do computer networking, you'll use a command line interface. And in 1980, that was the only interface. So Steve Jobs made it like this so we could use a mouse. And everybody stole his idea or copied his idea. When I say everybody, I mean, particularly Bill Gates. Because we got Windows 3.0, which looked like the Apple Mac. All right, so this term computing. In this course, we'll talk a lot about computing. We'll talk about computing, computational thinking. Computational thinking doesn't mean that you think like a computer. What it means is you think in a way so that you take problems and you structure them so that they can be solved using a computer. Does that make sense? So if you can do computational thinking, you'd be really good at being a computer programmer. But you might also be really good at being somebody who, you know, manages projects. You might be good at somebody doing human resource management. You might be good working in an accounting office because they also have problems, right? That can be solved, not always with a computer, but that can be solved in a step-by-step process that you'd use in a computer to do. So computational thinking is, we're going to spend a bit of time talking about that in this course. We're going to break it down into a bunch of different ideas that make up computational thinking, so that we can break problems into solvable sort of chunks. And so we're going to spend a lot of time with that. The word computing's been around a long time. Computers, as we're familiar with, this one here, and this one here, this is a computer. Those are computers. They've been around for a lot less. All right, so they've been around for I don't know, 50 years, 60 years. You'll see in the notes. 80 years, 1947. They've been around for 70 or 80 years, and the word computing has been around for a lot longer than that. And so when you said computer 100 years ago, you'd be talking about a person who's sitting in an office somewhere, you know, taking a bunch of numbers and adding them up. You know what I mean? They're a computer. They're computing things and they're adding and dividing. So a computer in those days might be somebody who works in the back of a shop or works with an accountant or something. They're a person, a smart person. They had to be smart because, you know, working with numbers, you can't sort of mess things up. A lot of smart people. We're so lucky because there's been a lot of smart people over the last couple thousand years, right? That made it a lot easier for us. Thank you for all those smart people. And some of these very smart people a long time ago, a couple thousand years ago, well, they came up with the abacus. I've already mentioned that. The abacus, I didn't know this. Anybody here from Afghanistan? So apparently there was abacus in Afghanistan. But of course, we know about it in China. And according to our notes, they had them a couple thousand years ago in Greece, or the Greek people. So have you guys ever seen anybody using one of these? People who know how to use it can do it really, really quickly. They can do all kinds of calculations just amazingly fast. They're just pushing things up and down. They're doing multiplication, division, that kind of stuff. So that was kind of a neat invention. So a bit more modern. So the abacus was pretty simple, but it's mechanical, right? You just got rods and you got little things that slide on them. If we got something that's a little bit more like a clock, if we broke this open, we'd see some gears and stuff inside of it, kind of like this. some gears and stuff inside of it, and the gears interconnect and work, on the base 10. So gears with 10 gears in them and stuff, whatever. And so you can use that to doing multiplication and division. So it's like a computer, but it doesn't plug into the wall. There's no electricity. It's a machine, but it doesn't have an engine. You got to sort of drive it with your finger, you know what I mean? You'd have to turn the cranks itself. So, but you could use it to do mathematics. Now, it was named after Pascal, Blaise Pascal, who was a French mathematician, really smart guy. He was a mathematician. He was a philosopher mathematician. So a lot of these really smart guys, just a few hundred years ago, they did a lot of stuff. I mean, not just mathematics. So he was mathematics, but he's making machines to do the mathematics, and he's also doing philosophy. You may have heard of Pascal's wager. I don't know. He was a really religious guy. But Pascal's wager was, well, a lot of you new guys, you guys here this is the Enlightenment period in Europe after the Renaissance. So there's a lot of people that stopped believing in religion because, they're saying, okay. And so Pascal said, well, he was religious. And he's like, well, you know what? His thing was Pascal's wager. What if there is a God and you didn't believe in him? Well, that would be bad for you, right? But on the other hand, if there wasn't a God and you didn't believe in him, well, that wouldn't be so bad. So maybe it's better just to believe. that was Pascal's wager. That's the bet that you're making. Maybe it's better just to believe because it would be really bad if there wasn't, you didn't. I don't know. So that's Pascal. You might like him for that. I don't know. Now Leibniz, he's a German guy, and also a really smart guy. I mean, so he made this engine, but he did other stuff too. So what was the other stuff that Leibniz did? Leibniz, at the same time that you may have heard of Isaac Newton invented the calculus. Well, guess what? Leibniz also invented the calculus basically at the same time, but he did it in Germany and Isaac Newton did it in England. I kind of like this story, so I am going to share it with you. Isaac Newton, I believe it was Cambridge University. He was at Cambridge University and they had a pandemic. Did you know they had a pandemic? This is not the first pandemic. They had a pandemic and they closed the university down. And so 2 years he couldn't go to university. So what did he do during his 2 years when he couldn't go to university? Oh, he invented the calculus. Something to do in your spare time, right? They didn't have computer games in those days. So he busied himself by inventing the calculus. All right, so there's this guy called Jacquard's loom. This guy called Jacquard, and he invented Jacquard's loom. He didn't invent the loom. The loom's been around forever, right? I mean, this part of the world, people make beautiful rugs. Not exactly here, I guess across, around here, yeah. Not very far from here. And they make beautiful rugs, and so they would do that on a loom. They'd have a sort of a frame that they would push some fiber across this way, push some fiber across that way, and you could do it by hand. Now, Jacquard said, well, maybe we could make that a little bit more efficient. We could do that quicker, especially for just ordinary cloth. And so what if we had a sort of computing way of doing that? This is before computers, but he punched out cards. I'm not going to pretend that I know exactly how he do it, but he got punched out cards with holes in them, and the holes lined up with different parts of the machine to have a fiber go this way or that way. So the holes in the card would make the fibers go in the right way. You've seen it. There you go. So it's a computer way of doing it. There was another one that was kind of like that, which was the player piano. I don't know if you guys ever seen those. They'd have a drum that went around, and the drum had little pins that came out of it, and the pins would cause a mechanical motion to make the piano play by itself. All right, so same kind of idea. By just having holes or pins, you can make something do kind of like a program. So like I guess you could say a song that it was playing is kind of like a program. And you could say that making a cloth is kind of like a program. Charles Babbage made a computer that is like a really, really fancy clock with lots of gears in it. Look kind of like that. And yeah, you turn the gears and you make the computer. The gears represent numbers, and you can make it do some calculations. So we call it a difference engine. Ada Lovelace. Ada, she's referred to here as the world's first computer programmer because what she did is she looked, I believe it was Babbage's engine. Correct me if I'm wrong if you do some research on that. But she's around that time and she's sort of coming up with algorithms. So we use the word algorithm, which is step-by-step set of instructions to answer a problem. And she did that, I believe, for Babbage's engine. Sorry, you had a question.
It seems that there is a kind of chemistry. You mentioned the word algorithm. Word related to scientists. How is it? He invented algorithm.
Did he invent algorithm or algebra? Algebra. I think algebra. Yeah, the algebra was invented by Muslim scholars 1,000 years ago or something like that. Yeah. You probably know more about it than I do, but yeah, could be. So yeah, algebra, which you have to learn. You guys are doing a calculus course, right? So you have to know how to do algebra before you can do calculus. And that was, I know that was invented by a Muslim scholar. So have fun with that. And the word algebra comes from this Algar, whatever her name is. I can't remember his name. Anybody name it? Algar. Yeah, something like that. I think maybe that guy. Yeah. Ada Lovelace, Ada Lovelace. There's actually a programming name is named after her, Ada. And so she's kind of well regarded. And I believe what she was doing was giving instructions for the Babbage's machine. Now, I'm not going too fast, am I? It's okay. Nobody's going to sleep yet, so that's good. The census in the United States was growing very fast as a country, still growing fast, but back those days, proportionally, it was growing really, really fast. So they're bringing in like 1 million people a year, and where are these people going, right? They're going to all these new cities, and way they do their politics there depends on how many people are in each area. They would give them a different, that was how they determined their congressional districts. That's how they determined if this new place could be a state, is they had to know how many people were there and what they're doing. And so everybody wanted to be a state. And so they needed to have details about that. And so they would do a census. We've had censuses here in Qatar recently, like last year. I had somebody come to my house and ask me information about who's there. So that's what they do. They collect this information. Well, what do they do with it? Well, now we just put it into a big computer program, and 2 days later, well, it wouldn't be 2 days later, a couple of weeks later or whatever, it is able to produce all kinds of reports. So back in 1890, not so much. Everything's by paper, right? It's a big mess. And this guy here, Hollerith, he said, well, you know what? That Jacquard's Loom thing, they had these cards. You could grab information from these cards. Maybe we do something like that with our information from the census. And so, yeah, he used these cards to make this thing that he called the Hollerith machine or whatever. And IBM company was built around that idea, and they were able to shorten the time necessary to analyze the census data. It used to take them 10 years, right? They do the census in 1880, then in 1890, you know what I mean? It would take them that long to get the results out of it. But he was able to shorten that cycle down to like 1 year, which is pretty good, considering now this is a computer device, you could say, but it wasn't electrical, right? So it's just using the cards and sort of using the idea from the pattern. And so IBM is a company that sort of came from that idea. And this picture here is supposed to represent somebody who's doing the input to produce the cards. So she's actually inputting the information that will be represented on the card. Now the card information is by holes in the card, and the holes in the right position is so. For example, in the census, that card will have numbers on it, but it'll also have other things about different categories, you know, male, female, age, all that type of thing, dress, all the kind of stuff that they gathered from the census. And so that was with the cards, the stack of cards, you could You could analyze where the holes were and sort of add up, big columns of holes, and you could get your information analyzed much quicker. And so IBM sort of grew out of that. And this picture represents a punch card from IBM. And as it says there, it was used from the 20s through the 1970s. And in fact, the first computer program that I ever did was at my first year at university in a math course. And we used the Fortran programming language, and we had to do it on cards like this. But the cards that we didn't have to do that hole punch thing where you typed anything. What we would do, I won't talk to him just now, I'll talk to him later. But what we would do is we would draw with a pencil. With a graphite pencil, you could just put a mark on it like that, and it was able to read the marks. And so that was kind of the next sort of step from that. That was my first degree. I started that in 1977, and so we were doing it with cards then. Well, okay, so very, very recently, people have been doing computer exams where they give you the exam and you give you a sheet of paper and you put all your answers on like that. Have you seen any of those? So same idea. I mean, but they were not reading holes, they were reading black marks. And so it's a quick way of doing the exam, right? So those exams, right, they take the paper and you got the answer next day, right? Because it's just A, B, C, D. Now, I think those are going to go away. And the reason why I say that is because D2L, right? We can do an exam. You're clicking, A, B, C, D, and the answer is immediate. And no paper. It's just all online. So I think it's good that we're not using paper because we've kind of messed up the planet a bit, haven't we? Maybe it'd be better if we didn't, we did some things without a lot of paper. Sorry? I hope you don't misunderstand me. I'm not saying that we don't need paper. I'm saying that there's sometimes that we can do things without paper. So let's do them without paper. So yeah, I mean, I'm using paper here. That's how I marked you guys in. But I don't have to. Like 2 weeks from now, if I organize myself, I can just do it on the computer. So, you guys seen this? Seen one of these things before? All right, this is a vacuum tube. And when I was a little boy, we had TV. Believe it or not, we did have TV back in those days. But when you'd turn on the TV, there would be a little white dot in the middle, and then it'd grow bigger, and then it'd fill up the whole screen. And that's because the TV had to warm up. It had to warm up, and these things had to get to the right temperature because they were the actual electronics of the computer. And each of these is like a single transistor would replace one of these. But they're big and they're hot, and they would blow up, and then you'd have to have the TV repairman come out and give you the thing, right? So these were our vacuum tubes. The vacuum tubes were like little gateways that we have in a computer. So nowadays, those are gone. Right? Nobody's using those anymore. So remember the picture we saw in an earlier slide that showed what was called the transistor radio? The transistors replace these. And the transistor is a kind of a small thing that has two wires, one wire on each side coming out of it, and got a little, not a conductor, what's the opposite? Insulator around it. And the transistor is a gate that replaces these things. And it's better, all right? It's better because it's more reliable. Then we talk about solid state. Solid state is going to include transistors. It's not going to have stuff that breaks easily. Now, the reason why I mentioned that is the space race. The space race during the 1960s, the 1950s, and the 1960s, we had a superpower confrontation in the world. between the United States and the Soviet Union, who were the victors of World War II. And so they were sort of lining up all over the world, but particularly in across the lines in Europe, where the Soviet Union had a lot of influence over the Eastern European countries, and the United States through NATO had a lot of influence over the Western countries, but also even in the Middle East. I mean, you know, you might have heard of the history of Nasser and all of that kind of stuff, and the very, very tragic history of Palestine. And all of this was sort of caught up in that. But how this confrontation was played out was not a fighting war, right? Except in those places where I mentioned. So the United States and Russia never went to war together. So what they did is they kind of like, you know, face off. Well, we think we can beat you. No, we think we can beat you. And of course they had nuclear weapons. But the other thing that they had is they had to have systems to deliver those weapons. And those systems had to be rockets, right? And some of those rockets could be launched by nuclear submarines, and some of those rockets could be launched from sites. And so that's what they had. And you got rockets that can destroy us. We got rockets that can destroy you. So we'll leave each other alone, that kind of stuff. I'm going to have to, it's got 10 minutes. So I'll just finish this thing and then we'll restart. But so this went into space. You can see why I'd go into space, because if you can send people up into space, then you probably got good enough rockets to send a nuclear missile over there, right? And so if I'm sitting in the United States and I see that the Russians send a satellite up and it goes around the world, and they did that in 1957, before the United States. They're like 3 or 4 years before the United States. So the folks in the United States are going, whoa, this is not great. You know, the Russians, they can put satellites that go all around the world. Probably they could put a nuclear weapon up there. It could come down on Washington. That'd be kind of bad for us. And so the United States is spending a lot of money to sort of counter that threat. And so what they said is, we'll go to the moon. We'll go to the moon. That'll prove that we're the big dogs. We can do whatever the Russians can do. We can probably do it better. We're going to go to the moon. And so the problem is, well, how do you get to the moon? You know, it's a long way away. It's 250,000 miles or something like that. And it's you have to get at this huge speed. And the other thing is you have to meet it at the right time, right? So there's a lot of calculations you have to do, right? You have to get your spaceship to go in the right place to just get with the gravitational force of the moon just enough so that you don't slingshot out and head off into space. You know, you got to get all of that exactly right. You can't make mistakes. So you got to have a computer, and probably you're going to have big computers on the ground, but you're also going to have a computer in that spaceship. Well, you're not going to be able to take up a computer that fills up a room, right? It's going to have to be a small enough computer that fits in that spaceship. And so they spent a lot of money making computers smaller. So companies that could do things that would make computers smaller, they gave them a lot of money. And the United States government gave a lot of money for the space race, a lot of money. And so they actually, the United States government basically funded these companies like Intel, Texas Instruments Semiconductor. They funded them a lot of money so that they could make these electronic advances so that we get small computers into a spaceship, so that we beat the Russians to the moon, so that well, whatever that reason was, who knows? Power politics, right? And anyway, so that turned out okay for us, I think, because the end result is we got stuff like this, which is an integrated circuit on a chip, which goes into a electronic device. Now, just a little bit about the integrated circuit. You mentioned chemistry. My first degree is in chemistry, and so something that I kind of like. And one of the things that we learn in chemistry, we learn about all of the different elements. You know, there's like 103 or 104. It changes depending on what they're doing in their laboratories, maybe 114 different elements that they've discovered. But one of the special elements is an element called silicon. And silicon is an element that when combined with oxygen, silicon dioxide, forms a material which is a semiconductor. And when you mix silicon dioxide with a pure silicon dioxide, when you mix it with a correct amount of germanium oxide or other semi-metal oxides, then you get this special matrix, which is a semiconductor onto which you can put a integrated circuit, which you can draw with an electron microscope device. And you can miniaturize your circuits to a huge amount, right? Very, very small circuits. So basically, you get like a whole computer that we used to have in the old days. You can get it onto this little chip. And the really good thing about all of that is that silicon dioxide is cheap as dirt. Silicon dioxide is dirt. So what I mean by that is most of the surface of the Earth, silicon dioxide is the most common compound on the Earth. If you kick a rock, pick it up, it's mostly silicon dioxide. All right, so it's not hard to find silicon dioxide. You go to the beach, you dig up some sand, there's silicon dioxide. Then you just have to purify it, get rid of the stuff that's not silicon dioxide, and then you have to dope it with the right amount of germanium oxide, etc. And then you can make a wafer, which is a chip, and you can draw a circuit on it, and then you've got the thing that's in the middle of that. And so, all right, the hard work there is the engineers designing the circuit, to get it to be the right configuration. But the easy work is in the factory making the chips, right? Because as I said, you don't have to go far to find the material to do it. Now, having said that, there are some rare earth metals that are required for our computer. I mean, we're using gold, we're using platinum, we're using a lot of special metals to do that. But the main thing is just our silicon dioxide. Yes, you had a question? All right, so fantastic. We can do all of this computing power in these very small devices. You're carrying around with you thumb drives that you store hundreds of movies on, right? Well, I don't know, not hundreds. Well, I suppose you can get gigabytes, terabyte USB. Hey, can you? I don't know. Yep, a lot. And we got these things. These things do a lot of stuff, lots of movies. This is a computer, right? It's a fantastic computer. And so even this would be old style compared to the stuff that's in here. I mean, we've got all of this processing power. There was a law about that was called Moore's Law. I don't know if you ever heard of that. But basically, the idea is that Moore determined in the 1950s that every 2 years or 18 months, the cost of doing a certain amount of computer processing divided by half, or for the same amount of money, you could get twice as much computer processing after 2 years. Alan Turing, I should mention, Alan Turing was a tragic individual. When I say he's a tragic individual, he died as a young man. He had a sort of a chaotic personal life. But he, and the reason why I mentioned that he had a chaotic personal life is because to give you the idea of at least what I think, people are so complex, right? We don't really know what people are, and there's a lot of potential in people that we don't really understand. And so, there might be this person who's a bit chaotic, but he might be a genius. And that was Turing. He was a bit of a genius. Anyways, he was able to come up with some ideas that were mathematical that related to computing, but he was also able to do a brute force sort of decryption of a code that was used by the Germans to communicate with their submarines. And so as a result of that, he gave the Allies a bit of an edge in the war that they wouldn't have had necessarily. And certainly that, now the Germans were never going to win the war because the thing was, how long is that war going to last, right? And so it would have lasted longer if he hadn't done that. German guy, Enigma. It's not that we got anything against Germans. Germans are awesome. And the next guy that we'll talk about is a German, right? Where is he? No. Yes. This guy. He's a German. If we talk about the space race, there was a lot of Germans there. There was a fellow by the name of Wernher von Braun. I don't know if you ever heard of him. Wernher von Braun. In 1945, he was building rockets that they were sending from France to England to cause chaos, to make the English not fight. he was captured by the Americans, and the Americans said, you know, this guy's pretty smart. We're going to take him back to America. And he became an American citizen. When the first men walked on the moon, President Nixon was talking to them. And beside him was Wernher von Braun, because it was Wernher von Braun's rockets that took the men to the moon. He designed those rockets. Now, he had some help, obviously, with scientists who were living in the United States already.
How about